All right. Hi, everyone. Welcome and good evening. My name is Seth Lewis, and on behalf of Harvard University Division of Science, Harvard Library, and the Harvard Bookstore, I'd like to welcome you to the latest installment in our Harvard Science Book Talk series. I'm thrilled to introduce this virtual event with PHILIP PLAIT, who is presenting his new book, Under Alien Skies, A Sightseer's Guide to the Universe. Joining him tonight in conversation is fellow astronomer and TED fellow Jessie Christiansen. Interestingly enough, tonight is not the first time our two speakers have shared the stage. In addition to the general overlap of their scholarship, Plait and Christensen both appeared together in a 2017 panel at the annual Star Trek convention, joining forces to take their audience on a science trek through the universe. And tonight, as they explore and converse about Plait's book, they will take us on a virtual trek of our own. Before we move forward, just a few housekeeping things to address. Next month, our final book talk of the academic semester will take place on May 3rd at 6 p.m. Chris Wiggins and Matthew L. Jones discuss their recent book, How Data Happened, A History from the Age of Reason to the Age of Algorithms. To stay up to date on all things Harvard Science Book Talks, make sure to subscribe to our newsletter, follow us on Twitter, and check out our YouTube channel for the latest videos. When tonight's talk begins, I'll place a link in the chat to purchase Under Alien Skies from the Harvard Bookstore. The format of our event is generally 40 to 45 minutes of conversation, followed by 15 to 20 minutes of Q&A. If at any point you think of a question for our authors, please click on the Q&A button at the bottom of the screen, and we'll get through as many of your questions as time allows. Lastly, thank you to our partners at Harvard Bookstore, and thank you all for showing up tonight in support of authors, publishers, indie book selling, and of course, science. Now, it's my pleasure to introduce our speakers. PHILIP PLAIT is an astronomer, sci-fi dork, TV documentary talking head, and all-around science enthusiast. The author of Bad Astronomy and Death from the Skies, Plait writes the Bad Astronomy newsletter and lives in Colorado. Joining him in conversation is Dr. Jessie Christiansen. Christiansen is an astrophysicist with the NASA Exoplanet Science Institute at Caltech, where she searches for, characterizes, and catalogs planets orbiting other stars. She is the lead scientist on the NASA Exoplanet Archive and has worked on the NASA Kepler, K2, and now TESS missions to characterize populations of exoplanets and to find and study the nearest planetary systems to Earth. Systems that will be perfect for further study with the next generation of ground and space-based telescopes. This evening, they will be discussing Plait's new book, Under Alien Skies, a book John Green calls a rollicking, wondrous, and awe-inspiring introduction to the universe. In this lively, immersive adventure through the cosmos, Plait draws ingeniously on both the latest scientific research and his prodigious imagination to transport you to 10 of the most spectacular sights outer space has to offer, in vivid, inventive scenes informed by rigorous science, injected with a dose of Plait's trademark humor. Under Alien Skies places you on the surface of alien worlds from our own familiar moon to the far reaches of our solar system and beyond. For the aspiring extraterrestrial citizen, casual space tourist, and even the curious armchair traveler, Plait is an illuminating, always entertaining guide to the most otherworldly views in our universe. We have a lot to learn this evening, so without further ado, I'm delighted to turn things over to our speakers. The digital podium is theirs.
Thank you so much, Seth.
Thank you.
Hi, everybody. I'm so excited to talk about this amazing book tonight. As Seth said, my name is Jessie Christiansen. I was lucky enough to get an advanced copy. You guys just wish you had this in your hands, and you can have it, I think, if you click the link that's about to appear. And it was so much fun to read, Phil. I had such a good time reading it.
Thank you.
So for folks who might not know, this is a bit of a turnabout of events for the two of us. Usually Phil is interviewing me for something about his writing, but now I get to interview Phil. So the microphone is in the other hand. Haha.
Yeah, and I've moderated you at what, twice on panel?
Yeah, multiple panels
at least
now.
Twice, yeah.
Now it's my job to get you to shush when we need to move on to the next question instead of vice versa.
Yeah, right.
But it's the day after your book came out. So first off, how are you doing? How are you feeling?
I'm tired. I'm okay. It's writing a book is a lot of work. It takes a long time. And then and then it's kind of gone. Especially when you submit it to the publisher with the illustrations, and then there's edits and all this stuff, and it's really sort of a maelstrom of work. And then you're done for a long time, months and months and months, and then suddenly they call you back and say, yeah, they call you and say, your book's coming out in 3 months, and now we need a list of people to send it to and things you can do. And so now it's been the past couple of weeks has been like setting up interviews and doing all that and getting this taken care of. So it's been a lot, but it's been a lot of fun.
Of course. And I hope it continues to be fun as you get to like enjoy the fact that the book is out. So let's talk about how the book came to be. You mentioned at the start of the book that you originally wrote a much shorter version of the idea for Under Alien Skies for an article that you wrote, where you go to 3 of the locations, and this book obviously is expanded to 10 locations throughout the galaxy. But I'm guessing the ideas were spinning in your head for even longer than that. Do you remember the first time you really found yourself trying to picture what the sky would look like from a different place?
Wow, that's 2 different things. I started
Choose either of them to answer.
the last part. Yeah. I mean, I've been doing that all my life. You and I are both Star Trek nerds, and I grew up watching the original series. It was already off the air, but pardon me, it was on endless repeats, and so I was watching TV shows like that and a bunch of other science fiction shows and movies, and so I was always sort of thinking, what would it really be like to be on these places? It'd be so cool. The idea for the magazine article, I wrote that for Astronomy Magazine, and it was published in 2003. So it was 20 years ago. It took 20 years to get this book basically out. I had other ideas, I guess, that had to come out first. And that was an interesting experience because it didn't go quite the way I thought it would. When I take my telescope out and show people what the skies look like, or giving talks and showing, or just writing about Hubble Space Telescope images or whatever, the question I get all the time is, would these things really look like this if you were there? Mm-hmm. And I think, no, because you'd be dead, period. And then we're done. Right. But in fact, some of these things, you look at Saturn, you look at the moon, you look at Mars, sure, they're going to look a lot like the photos you see, especially from spacecraft. But then you start looking at some of these other objects like gas clouds, nebulae in space and things like that, and they don't. And that actually took a lot of work, a lot more than I expected when I first wrote this article. But then, these ideas were just sort of floating around in my head. And I always wanted to write this into a book because it's the universe, it's huge, it's full of stuff. And I wanted to write about it all. But I'm lazy. I never got around to it. And I had other books I wanted to write first and other things to do. And then we wound up, I was talking to my agent, and we pitched this to a couple of different publishers, and Norton said, hey, let's go for it. And then it took me 2 years, actually, to get this thing written. Turns out having a full-time job and trying to write a book at the same time, a little bit tough, a little bit tough.
But I really understand that feeling of an idea kind of bubbling to the top and getting to the point where it has to come out, right? Like it's spent that time, churning about, maturing inside you, and then finally it's like, no, it's ready. Like, let's go. It's good. It's a good time.
I'm sorry, I'm laughing because that's a good synopsis, but in detail, it's a little bit different than that, because you can be halfway through the book and you're writing a chapter and you're going, oh God, this isn't working at all. This is terrible. And then and this happened with both of my previous published books. Halfway through a chapter, it's like, this just isn't going to happen. And so then you're in a panic. It's like, well, now I got to write something different. In this one, it was more along the lines of, what am I going to write about? There's so many things to choose from. So I had this huge list and I was crossing things off. And I thought, well, I want to write about asteroids, but I also want to write about comets. Should I put them together? And the answer turned out to be yes. And then even as you're writing, you're realizing it's like, oh, this is going in a different direction than I thought it was going to go, but I like it. The comet chapter, I had this idea in my head. And by the time I was, 2,500 words into 5,000 of that part of the chapter, I realized, this isn't going in the same direction, but I'm enjoying writing it this way. So, you have to be a little bit flexible and
right.
Write about what's coming.
So for
It's
folks
coming
who
out.
haven't read the book yet, Phil starts kind of locally and then moves out through the solar system to the edge of the solar system and beyond. So we get to asteroids, we get to Saturn, we get to Pluto. Contentious, I know. But you mentioned that you had this huge list. So actually, one of the questions I was curious about was what got cut? What didn't make the book that you were sad that you didn't get to write about in the end?
I actually covered, I think, the kind of things that were the kind of things the public wants to know about. I mean, that you want to write something that your audience is going to read, but also the kind of things I really wanted to talk about. So I covered mostly everything. But there were things like, what does a galaxy look like when you're floating outside of it? And one of the questions I get a lot too is, especially when I'm talking about other galaxies, is how do we know that we live in a galaxy? How do we know that we live in a spiral galaxy? And we're inside it, and we can't go outside of it because it's too far to go. So how do we know this, and what would it look like? The how we know this part is actually pretty easy, but what it would look like is actually a little bit tough, tougher than I expected. I had some notes on this, like, do I want to write about this? And then I realized I'm not 100% sure how to do this because our view from Earth is very different than it would be out in intergalactic space. There are dust clouds and things that block our view of a lot of the galaxy. And just figuring out, would it be brighter? Would it be dimmer? Would it be about the same? And then as I was writing it, I realized it's not, I don't want to say it's not as interesting or engaging, but it's just not different enough from the pictures you see to make me really want to write about it. And I thought, I want to write about a black hole. I want to write about being in a gas cloud. I want to write about, especially I want to write about a planet around binary star, around two stars that orbit each other. And then between the time I originally thought about writing this and I wrote it, red dwarfs became a thing, these little tiny stars that are very cool and faint. And then we find out that they're really good at making planets. And it turns out these planets are very different. They're reminiscent of our solar system, but very different. And as I started thinking about it more and more, I realized, oh yeah, I really want to write about that. And that kind of threw the galaxy out, and near a pulsar. I
like the idea that there was this like bracket where some things just like didn't make the cut.
It's kind of like that. It's you've just got so much, you have so much room in your head. Like I can still remember my phone number from when I was a kid, but I can't remember the name of somebody, like a friend of mine I used to have in college. Things get pushed out and things stay in. And in this case, the red dwarf thing, once I realized I wanted to write about that, it pushed everything else out. That was the next contender.
Could you talk more about your process for, once you chose a place, how did you do the research? How did you put your mind there? Like, how did you come up with these imagination things?
That's, this is one of those questions. How do you come up with your ideas? It's like, well,
I mean,
I'm in the shower.
Did you read a lot of academic papers, or did you read a lot of popular science books, or did you where did you go for your information? That's
a good question. I did read a lot of journal papers. Oh my God. And for my last book,
on behalf of publishing astronomers.
Yeah. Oh, and thank heavens, let me tell you, because for my last book, Death from the Skies, about astronomical disasters, that was this was in 2006 and 2007 when I was writing that. And so the internet wasn't what it is now. And so being able to find papers was a little bit tougher, and I had to print them out. And so I had a stack of papers, like this when the book was done. If I had done that for this book, that stack would be huge. It was mostly along the lines of, for some things like the moon, it wasn't that hard to come up with ideas because I've been a fan of the Apollo missions my whole life. I actually watched Apollo 15 launch when I was a wee little lad.
In person?
Yeah, we went.
Wow.
My family went to Florida, and I stood there and watched the rocket go up. And so, writing about the moon, the idea of how would you walk on the moon? What would a habitat be like? And a lot of that is just informed by the knowledge I've accrued over my years of being an astronomer. And also, then it was like, well, I also know that, for example, the surface of the moon is covered with this powdery dust called regolith, which is really just ground up rocks. And it's not like dirt. People call it the soil of the moon. It's like, no, soil and dirt are different. That's that has organic stuff in it, bacteria and everything. This is really just ground up rocks, and it's mostly like volcanic ash. And you look at the stuff under a microscope, and it's a horror show. And that's actually the word I used in the book, because it's jagged and spikes sticking out of it. And if that stuff gets in your lungs, it's a real problem. And if it gets into machinery, it can screw it up. And if it's this really nasty stuff. So I wound up reading a lot of papers about, you know, what are the effects of that? How can we use it? There are these ideas now, it's mostly coming from the European Space Agency and groups over there, that are figuring out ways of scooping this stuff up, heating it up and turning it into bricks. And then you can make it into a habitat. So you don't have to, you don't have to haul your plywood and sheetrock and everything with you. You can build the materials there. So there's a lot of like just stuff I knew plus stuff I thought about and read about. And then when it came to something like planets around a red dwarf or planets orbiting a binary star, I had to read a lot of papers. I had an idea, like the geometry of this, but then thinking about literally, how does the gravity behave? How does if you're on we can get to this a little bit later, but if you're on a Tatooine planet, Star Wars, and it's orbiting binary stars, what happens to your temperature of your planet as you're going around these stars and the stars go around each other? And then I wound up doing a lot of math.
I really appreciated the parts where you like step by step worked out what the seasons would be for these multi-star systems. It got
you
very
like that
complicated.
part?
Yes, no, I enjoyed it.
I was worried about that because it's like, is this too much detail? I don't know,
not
because
for me.
it's weird, but it's kind of cool. It's like, if you have a planet, let me back up. If you have two stars orbiting each other, and you're orbiting both of them, so it's what's called a circumbinary planet. It's a lot like orbiting one star, but a little different. I mean, you're orbiting both of these stars at the same time, so you can still have seasons. You have a day and a night, but there are weird things to see. I mean, if you think of Luke Skywalker standing on Tatooine with the wind going through his hair, and the French horns are playing in the background in Star Wars, that scene was pretty accurate. That was really quite good how that was set up. But there's another kind of binary system.
And I want to point out, 20 years before we'd found any planets around other stars, George Lucas is already like, hey, what if there was one around two stars? Amazing.
And that came out in 1977, I think.
Yeah.
So yeah, it was a long time ago. There's another kind of binary system. Well, you still have two stars orbiting each other, but this time they're really far apart. So you have a planet orbiting one of those stars while the two stars are going around each other. And it turns out that's really different, because you can have your seasons and everything like normal, except that over the course of the year, that other star that's orbiting around the star that you're orbiting around can be up at, say, midnight sometimes for some part of the year, and other times it's up at noon. And so you have two stars in the sky, two suns in the sky. And sometimes, your sun sets and then the other one rises, and that means you don't have nighttime for a long time. And as I sat down and tried to figure that out, it became a whole thing. And I had to have diagrams for it. And I thought,
the diagrams are helpful.
Yeah, the diagrams are great, by Chris Jones, my illustrator. And he did a really good job. We had to go back and forth with this a lot. And oh my God, was I panicked about that. Like, I had to check it over and over and over again. Like, okay, so it's spring, and your primary sun is rising, your secondary sun rises at midnight, and I have to make sure. And I panic about details like that all the time. Hopefully it was correct.
Yeah, I didn't double check, but it read fine. But like here, where we have the months have the almanacs, like the flower moon and the wolf moon and the harvest moon. You could imagine, like, if you were an exoplanet orbiting in one of these double star systems, you can't just have 4 seasons, right? You have to have like the double summer, the spring summer, the et cetera, et cetera. You've got these hybrid seasons.
And it was interesting thinking about that, because you could tell your seasons by the other star. If the other star sets when your star rises, you could call that the first day of fall or whatever. And I talk about how astronomers talk about this. When they're together in the sky, that's called a conjunction. When they're opposite each other in the sky, that's opposition. So I use those terms to talk about the seasons. But that's one kind of season. But if you're thinking about seasons like spring and summer and winter, yeah, your planet could be tilted and you'd have seasons just like Earth does, but that might not relate to when the other star is in the sky. And that's where I just kind of said, yeah, to heck with this. That's just going to be that's a disaster. If you have a calendar and you're living on a planet like that, I'm going to leave that to you because I don't want to try to have to figure that out.
Right. Well, and one of the things I liked about that section is the way you're imagining, what life is like on one of these planets. So for instance, one of the things you talk about is tidally locked planets. So the planets that are orbiting the small red stars always have one side of the planet facing the star and one side facing away. And whenever we talk about these as potentially habitable planets, there's always this pushback, but like, how could life survive on a tidally locked planet? It's always daytime on one side and always nighttime on the other. And I'm always like, imagine if you were life evolving on the day side of one of these planets and you were looking at this planet that's revolving and every 24 hours as it's going around its star with these massive temperature swings and illumination swings. That sounds crazier than just, hey, the temperature and the light is always the same. Go bananas, evolve, do what you want to do. Like it's
exactly
truly
right.
alien, right?
And I was thinking that when I wrote that chapter, because if you look at Earth and you say, oh my gosh, I mean, a quarter of the atmosphere is made of oxygen, which is a highly reactive molecule. It's terrible to have around. And water, oh my gosh, water is a mess. It dissolves things and and it freezes and expands, and it's a disaster for life. But in fact, life evolves to the conditions you have there. And these planets these tidally locked planets, if you're not familiar with this idea, you're familiar with at least the overarching concept, because the moon is tidally locked to the Earth. And I'm talking to the audience here, not you, Jessie. I'm sure you're familiar
I'll take a drink while you do that.
The moon. Because of the way the gravity of the moon and the Earth have interacted over their lifetimes, the moon spins once for every time it goes around the Earth. And so it's always showing the same face to the Earth. And planets can do this when they orbit stars as well. And so you have one side which is perpetually daylight and one side is perpetually night. And it turns out, that can be a problem if you're close into the star, you don't have an atmosphere, say, then one side of the planet gets infernally hot and the other side is incredibly cold. But if it has an atmosphere, the heat from the day side can then flow around. It's sort of always windy on this planet because the hot air rises on the day side and then flows around to the night side. That cools off, it warms up the night side, and then that cooler air flows back to the day side and cools it off. So it may not be as bad as all that. And when I talk about this planet orbiting this red dwarf star, it's called TRAPPIST-1, and the star is a real star. It's only 40 light years away. It's quite close. And it's so faint, though, you need a huge telescope just to see it at all. These stars are really dim bulbs. But I had this idea of, you land on this planet and what do you see? And it's like, well, the sun is always there. It's just there. That's where it is in the sky. It never rises and never sets. And it's always windy. There's always wind blowing in one direction because the wind is blowing from the day side to the night side. And where the terminator is, the line between day and night, the temperature drops so much. You have this moist air coming from the day side, cooling off on the night side. It's going to be perpetually stormy there too. And so, I'm not a meteorologist, I'm not a climatologist, but that just seems kind of logical. And I bet that's going to be at least an idea of what these planets are really going to be like. And when you get into the details, of course, it's going to be a mess. If they have oceans or continents, it's going to change all that. But it was fun to just imagine that and think, what is this going to be like for real? And something that occurred to me it just occurred to me, I'd never thought about it before, but the sky on that planet, if you have a planet that's just like Earth, but it's orbiting a red dwarf, the sky won't be blue because there's no blue light coming from the star to light up the sky and make it blue. So the sky is going to look very dark. It might look red, maybe, but more likely even during the day, it's going to be black. And it's not because there's no air. It's just that there's no blue light coming from that star. And I thought, I've never seen that displayed in an article, a book, a TV show, nothing. And I thought that's pretty interesting. And it was kind of fun to write about that too.
Oh yeah, for sure. Speaking of TRAPPIST-1, one of the things I really enjoyed about the book was that you didn't just take us to special places you took us to special places at special times when things would happen that we don't see from Earth. So TRAPPIST-1 had this really cool example. Do you want to talk us through something you would see from the planets of TRAPPIST-1 that we wouldn't see from Earth? I'm
You mean
thinking
the
of
planets transiting?
the double transit. Just super cool.
Yeah, so you've got this little dinky red dwarf star, and it has 7 planets orbiting it. And so they all orbit in the same plane, kind of like our solar system does. All the planets orbit roughly in the same plane. If you saw the solar system from the side, it would look like it would look flat, and all the planets would orbit together. It's the same thing for TRAPPIST-1, and in fact, that's how we discovered these planets. We happened to see those planets orbiting edge on, and so once in orbit, they pass directly in front of their star, and we don't see the planets, but there's a dip in the starlight. It gets a little bit dimmer, and that's how they were discovered. So if you were on one of these planets, let's say planet E, which is, let's see, B, C, D, E, the 4th planet out from the star. I have to count on my fingers to do that. We name the planets in order of discovery, but in this case for TRAPPIST-1, they were discovered in order from inside out. So the innermost planet is B, the next one is C, D, E, F, G, and H. I think I got that right.
Yes.
And so if you're on planet E, B, C, and D can all transit the star from your viewpoint. So these are like mini eclipses. And I talk about that as you're approaching the system, you see the transits, you see these planets passing in front of the star. But then when you're on the planet, you see it as well. And it happens a lot because these planets, to be warm, well, let me rephrase that. These planets happen to be huddled very close to the star. And if you have a planet that's going to be Earth-like, it has to be close to that star because that star is very cool and faint. So it has to be closer to be able to get the heat to keep it warm. And so these planets orbit the star in a matter of like hours and days. So you will see these transits happening all the time, including sometimes you'll see 2 of them passing in front of the star at the same time. And it was so much fun to think about that. This is so different than what we see from Earth. Mercury and Venus can, in fact, pass in front of the sun, but they're rare events, especially a Venus transit. That doesn't happen very often at all.
Has there been a double transit of Mercury and Venus?
Like, there has been.
History? Like, it should technically have happened.
I read about this, and it's extremely rare, and I can't remember the timing, but it's like every, it's on the order of thousands and thousands of years, if not longer. So it was a long, long time ago. But yeah, Mercury and Venus could technically, I think, could transit the sun at the same time. Venus, the geometry is a little weird because of the tilts of our orbits and all kinds of stuff. So it happens every like 108 years or something like that. But then 2 of them happen.
Yeah, they happen in pairs.
They happen in pairs, 8 years apart, and then 120 years between them, or something like that.
Yeah.
But
I
on
just love
TRAPPIST,
this description of TRAPPIST-1, where it's like truly alien in the sense. So for us, the sun moves and the planets kind of really slowly move. But if you were on TRAPPIST-1, the sun stays still and the planets are all moving back and forth. Like just it's the opposite, and such a weird idea.
I should probably, when I do these video talks, I should probably have my notes from when I was writing this chapter, because I have all these diagrams of like how far out from the star they can get. And I did it all by math first. I know how big the orbits are, so I can calculate using trigonometry what they look like. But then it's like, great, I have these numbers, but I have no idea if I did the math right. So what I would do is I would draw things out to scale and check it and make sure it was right. And some of these transits, it's not just like a dot moving in front of the star. It's actually big. Right. The star is small. And the next planet in is big enough and close enough that it actually blocks out a lot of the star's light. So the star is always in the same part of the sky with the planets going around it. And you see these eclipses all the time. And just even thinking about that was totally wild. And one of the things I really, really, really wanted to get across in this book is that these places are real. Now, I pretend that we're in a spaceship going through a gas cloud or near a black hole and stuff like that, but I based it all on real objects. And in this case, I'm writing about TRAPPIST-1, a star we have discovered with planets we have discovered. And I did all the math according to the numbers that we have, which are pretty good, about the sizes and distances of these planets. And so it reads like science fiction, but this is a very real place. And you're the keeper of the exoplanet database. The queen of the database. we've discovered how many planets now or have been confirmed?
5,332, and tomorrow it'll be 5,339.
Right? That's a lot.
A lot of planets.
And how many of them orbit binary stars, for example?
Yeah, so I just checked this today. It's 483. So nearly 10% of the planets we found are orbiting stars where they're either orbiting the two stars close together and they're going around, which is the circumbinary situation you talked about, or they're orbiting one star in a multi-star system. And I'm not just talking about two stars. There's systems of 3 and 4 and more stars, hierarchical systems.
Right. So cool. Almost 10% of all the planets we've discovered. And I don't know if there are effects, because I don't know if
there are. It is harder to find them around multiple stars for various reasons. So that's a lower limit. The actual real numbers of the real planets in the galaxy is higher than 10%.
So, okay, that's what I would have figured, because of the way we observe them, right? But in fact, the nearest exoplanets in the entire universe to Earth, to the sun, are in a trinary star system. They're orbiting the star Proxima Centauri, which is a red dwarf orbiting two more or less sun-like stars. So you have these two stars going around each other, a red dwarf going around that pair, and at least two planets orbiting that red dwarf, and maybe a third, but it's super, super hard to detect those planets. So again, these binary star systems I wrote about, these are real. There are real planets orbiting these stars. So over and over again, I just kept thinking as I was writing this, I'm making this stuff up based on really good science, but these places are very real. And so for me, what I really wanted people to understand is, yes, they're real, but also to immerse the reader in this experience. So it's not just like on the moon, it gets very hot, it gets very cold, and the sun, the day takes, sun rises and sets, it takes 2 weeks and all that kind of stuff. I really wanted to be like, you are here. And you look around, and what do you see? What do you feel? What do you experience? And that part of it for me was really, really fun to write. I guess I'm a frustrated science fiction writer. And so being able to do that really satisfied this need I had to be a Star Trek fan fiction writer or something like that, and say, here we are, what's it going to be like?
Right. Well, so for all of the Hollywood script people out there, contact Phil. He's got ideas for you. So I know you were trying to talk about what in the book is real. So for people who might not know, Phil, a lot of your early science communication career was based on debunking things that weren't real. So was there anything, was this book an excuse to set the record straight on anything in particular for you? Were there any like pervasive misconceptions that you were like, no, we're going to get it right?
Not as such. I mean, my first book was called Bad Astronomy, and it was debunking a lot of stuff about that. And in this case, it wasn't, I didn't really set out to do that. The one thing that springs to mind is the idea that if you're standing on the moon, and this is an old idea, because the moon is tidally locked to the Earth and spins once for every orbit, the Earth is sort of nailed to the sky. Wherever you are on the moon, if you can see the Earth in the sky, that's where it always is. It's that direction. And it turns out that's not really true, because the moon's orbit is elliptical and tilted with respect to Earth's equator. And so it actually, because of perspective and things, we can actually from Earth see a little bit onto the far side of the moon in every direction, north, south, east, and west, depending on where it is in its orbit. And what that means, if you're standing on the moon, is that the Earth is actually going to move in the sky. And so that was sort of it's not like people walk around thinking, well, I guess if I were on the moon, the Earth would always look in the same spot in the sky. Nobody thinks that, right? But it's sort of this idea that's pervasive amongst science communicators and astronomers. And it's not right. And as I thought about it, and I started doing the math, and I thought, okay, well, the moon does this and this, and how much would the Earth move? And then I realized, oh, this math is super hard, a lot harder than I thought it was going to be. And I wound up going and using planetarium software and say, okay, I'm on the moon, show me the Earth. And the Earth moved a lot. And it was like 15 degrees, which is...
That's a big chunk of sky.
It's like bigger than your fist when you hold your fist out like that. So the Earth isn't just sitting there, it's actually making this complicated elliptical motion. Mm-hmm. And that really surprised me. I didn't think it was going to be anywhere near that much. And then I realized after I did that, oh, that means that if you're on the right spot on the moon, you can see the Earth rise and set over the course of a lunar orbit, 1 month. And so I put that in the book, and it's like, that wasn't something I set out to do. But once I saw that it was a thing that actually happened, and again, it was one of those things where it's like, that's so weird. I had to check it like 5 different ways, but I always wound up with the same numbers. So I thought, okay, this must be real.
Right.
And it's like, that's pretty cool. That'd be a really fun vacation spot. You go to the moon for a couple of weeks and watch the Earth slowly rise and slowly set over the horizon. That'd be pretty awesome.
Yeah. I liked the vacation destination recommendations for, the sometime in the future when we have comfortable, safe, faster than light travel.
Yeah,
the reason I was asking about setting the record straight, one of the things that I read in the book that genuinely surprised me was if you were standing on an asteroid in the asteroid belt, you wouldn't be able to see any other asteroids. Like, I'd literally never thought about it. Like, and I know that everybody thinks the asteroid belt is super crowded and you've got all these, science fiction shows of ships like dodging through the debris. But I'd never thought about the fact that it is so empty. If you're standing on an asteroid, you can't see any other asteroids. That really, I like genuine shock there.
Yeah, there are so many asteroids. I mean, we already know of something like 1 million that orbit the sun between
like
Mars and Jupiter.
That's a lot.
Yeah, I mean, and those are the ones we know.
Exactly.
And of course, we've discovered all the big ones. And so the ones we're finding these days are smaller, a few miles across or less. And if you talk about how many there are, you have to define how many are there bigger than a certain size. So how many of them are there bigger than, say, 100 meters across, the size of a football field, say? And it turns out there are a billion of them bigger than 100 meters across. This is such a huge number. And you think it must be like Empire Strikes Back when the Millennium Falcon is shucking and jiving in between these things to get away from the TIE fighters. And it turns out, no, it's not like that at all, because these things are small, and that is a lot of real estate out there. And it turns out that if you do the math, you can stand on the surface of an asteroid and look up in the sky, and there won't be a single one visible to the naked eye. That's not always the case. I mean, you may be near enough one, but in general, on average, they're really far apart. I wrote about that in my first book. Because I was talking to a friend of mine who studies asteroids about that, and he told me that, and I couldn't believe it. And then I thought about it some more and just did, kind of really like high school level math and went, oh yeah, that's right. They're really far apart. And I did it again to make sure, because you never know. I may have screwed something up in my first book, but I
feel like instead of A Sightseer's Guide to the Universe, the subtitle should be Filled in the Math.
Yeah. Well, yeah. Don't trust my math, because believe me, I found I did for the binary star planet, and if the two stars, if you're on a binary star planet going around both stars, the stars are going around each other too, and so every now and again one star will block the other one, and when that happens, you're not getting any light or heat from the star, which means your temperature is going to drop. And I thought, well, how much is it going to drop? 20 pages of algebra later, and I finally had the right answer, because I screwed up that math at first. I used some math I knew from graduate school, got the wrong answer. I just like this. I know this can't be right, and had to back out of those equations and derive them from first principles, which is not something I've done for 20 years until I finally figured out what I was doing. And so,
yeah, that would have taken me a beat as well.
What a nightmare! But
and now you have the answer.
Yeah, and I spent hours, over a course of days figuring this out, and it's like 2 paragraphs in the book. But those paragraphs are good.
But you did the math so that we don't have to. So
right, exactly.
We just get to read the answer and go, and then keep going.
Pretty much, yeah. And that happened a lot for this book. Some of the things were so strange, like if you land on a rubble, these small asteroids that we visit are not solid rocks.
The scene where the person just goes into the debris.
I know, and it was like, and I had this idea. Well, let me back up a little bit. I know we don't have a huge amount of time, so I'll talk a little bit more quickly. So when I was a kid, we thought that asteroids were like these giant solid rocks, like a rock you'd find in your garden, but they're not. They're actually, the little ones are rubble piles. They're basically collections of zillions of rocks held together by their own gravity. And it's not 100% clear why that is. It could be that these things suffer impacts that crack them, and over time they just crack all the way through. Sometimes they get hit hard enough to basically explode, but then their gravity pulls all the stuff back together again. So it's just a rubble pile. But the thing is, in a lot of cases, these rocks are so fragile that if, even though some of them are huge, we see on the surface of these asteroids, like the size of a house, if you had that rock on the Earth, it would collapse under its own weight. They're very friable, as geologists say. You could just crush them in your hand. And so if you tried to step onto the surface of an asteroid, these rocks would crush underneath you, and you could actually fall into the asteroid. Not because of the gravity, but if you like jumped from your spaceship and tried to land on this thing on your own 2 feet, you could just fall into the asteroid. And we saw one of our spacecraft do this. It was getting up to the asteroid to get a sample to return to Earth, and it actually buried itself about half a meter, about 18 inches into that asteroid before it stopped and pulled itself out. And I don't think anybody was expecting that. I think they thought it was just going to touch the surface and bounce off, and it didn't. And if it hadn't have basically used jets to puff gas out and blow itself in the other direction, it just would have gone straight into that asteroid. And I had to write about this and talk about trying to visit an asteroid, actually falling in and getting stuck in there.
All right, as you mentioned, we're starting to run short on time, so I want to make sure we have time to get to questions from the audience. So please, if you have questions for Phil, put them in the Q&A. I really like this first one because it's going to give us a chance to talk about something we both enjoy talking about. Philip asks, why is the sky red on Vulcan?
Well, Vulcan's not a real planet.
But it's a planet that we love.
Yeah, it's a planet that we love. And for a while, we thought it was a real planet because a planet had been discovered around the star that is canonically Vulcan's star in Star Trek. And we're all very excited about this. But then just a couple of months ago, a paper came out basically saying, yeah, no, it's not real. It was an artifact of the way it was imaged or observed. So that was a sad point. But the sky color depends on a lot of stuff. It can depend on the color of the star. It can depend on what's in your atmosphere, like gases, like we have nitrogen in our atmosphere that's really good about taking the blue light from the sun and sending it all over the sky so that everywhere you look, you're seeing blue light coming at you. But on Mars, for example, there's a lot of red dust in the air. It's literally rust. It's iron oxide, and it's very, very fine powdery particles that float in the air of Mars, and it tints the sky red. And there's also another effect, and I talk about this in the book, because our sky is blue during the day, and then when the sun sets, various physical things go on that make the sky look red, make the sun look red when it's setting. But on Mars, it's the opposite. This dust makes the sky look red during the day, but when the sun is setting, it's actually, that dust is really good about sending that blue light toward you. And so the sky around the setting sun looks blue. And you can see this in photographs taken by rovers on the planet. And so it's the opposite of Earth. And it could be the same with Vulcan. Vulcan in the TV show is very hot. It's probably got a lot of desert. And so maybe there's a lot of dust suspended in its atmosphere. And that's why the sky is red. So there you go, just like Mars.
Or you talked about Titan in the book as well, which, there it's tholins making the skies look, a darker orangey reddish color rather than iron.
Right. Titan is the largest moon of Saturn. It's the only moon in the solar system that has a thick atmosphere. It's mostly nitrogen. But the sunlight hits these molecules of methane and stuff like that in Titan's atmosphere, breaks them down, and then they reform into more complicated molecules. And a lot of these things are red or brown or yellow. And Titan looks really orange from a distance. And if you were on the surface and looking up, the sky would be sort of a dull yellowish orange color. So yeah, that's a good point. It just depends on what you're seeing, what's in that atmosphere.
And when you look back, like you mentioned, watching the original series, it's amazing how many fictional planet surfaces just look like Southern California with a slightly different filter on the lens. Right. Just here's green and here's slightly purple and here's slightly orange. They're alien, but yeah, and I remember the skies are all different colors.
I remember one episode that had a green sky, and when I was a kid, I thought, well, that's silly. And now I'm like, I don't know what would make a green sky now as a scientist, but I wouldn't discount it because heaven knows nature seems to be a lot more clever than we are. And just even in our own solar system, stuff is so weird that you never know what might actually be going on out there.
Yeah, well, I mean, that was actually one of the questions I had, which was, now that we've discovered all of these planets around other stars, one of the things we're discovering is how different they are from the planets of our solar system, like in different sizes and configurations and temperatures and around different kinds of stars. And I wondered if you wanted to describe, like, since your career has spanned before the discovery of exoplanets through to the discovery of thousands of exoplanets, like how that's changed your perception of us and our place in the galaxy.
Hey, you kids these days always had planets on other stars. Yeah, I was in graduate school, just starting to work on my PhD with Hubble when the first planets were discovered around other stars. And I'd already gotten my PhD in 94. I can't remember what year it was. And a year later, planets were discovered around stars more like the sun. And as we started to finding more, I mean, that was such a huge thing. And you read books about big discoveries in astronomy. We've discovered the universe is expanding and all this stuff. And you don't really know what it's like to live through a revolution like that. And for this one, it was amazing because we didn't know if planets orbited other stars. And then all of a sudden we found them. And to see astronomers yelling at each other, these aren't real, or, could be this, could be that. And nobody really knows. And then I won't go into the details, but you can read about this in history books now. But I remember just hearing about it from somebody saying, "Oh yeah, they confirmed a transit of a planet around another star right when it was predicted," and it was like overnight. Everybody was like, "Oh yeah, these are real. These are planets." And then to realize that they're around stars that we can see. Some of the first planets found are around stars bright enough that you can see them with even binoculars of the naked eye. And then I realized it's like you could use an off-the-shelf telescope. You could like order a telescope, a small, backyard telescope and a camera, and detect these planets. Now your detection wouldn't be that great, but you would be able to see it. Mm-hmm. And that to me blew my mind. It's like these have been hiding in plain sight forever. And then it just happened to be that we started to discover them, and then everybody realized they're everywhere, and we could have been spotting them this whole time.
Right. So I did laugh at I think I actually took a picture of the line in the book where you're like, transits are easy. It's so easy to find. Like, I spent my entire PhD trying to find transiting planets and failed. From the ground through the atmosphere with the sun rising and setting every day. It is.
You're just not very good at this. I'm sorry to tell you this, but if you had just bought an 8-inch telescope, no, I mean, of course it's hard to do if you're doing it if you're looking at faint stars or planets that are too small. I mean, there's a million reasons this is hard. But for those first planets that we found, and we observed one with Hubble, and it was this beautiful, we got this gorgeous graph out of it. It was so perfect and smooth and lovely. And then somebody actually posted one on the internet that they'd taken from their backyard with a small telescope. And it was ratty and noisy and everything, but it was there. You could see it. And to me, that's the part that just totally destroyed me. It's
and for everybody on the line, if you have a telescope, there are ways that you can get involved in helping us confirm planets that, for instance, the NASA TESS mission is finding right now. There's this huge network of ground-based amateur astronomers with their backyard telescopes who are able to do this, who are able to take these really simple measurements. But, we need the complementarity of like the space and the ground to actually confirm these planets. So if you have a telescope and any of this sounds exciting, there are ways to get involved. I have another question from the chat from Christopher. On a spinning planet, what limits the height of mountain ranges other than geological factors? Does planetary spin encourage higher mountains?
Ooh, that's an interesting question, and I've never thought of that before. But okay, in general, it's not that big of an effect. You're talking about mountain building, and I can see the Rocky Mountains out my window here. They get so tall because of two things, basically. Gravity. If the gravity is too strong, you just can't make big mountains. And the structural strength of the material the mountain's built out of. So on Earth, you can, granite, which is, not the strongest mineral, but tough enough. You can have mountains that get to be several miles high. On Pluto, where the gravity is lower and water freezes so solid, it's actually harder than granite. You can have mountains that tall made out of water ice. But on Earth, you can't do that because the ice just isn't strong enough to support its own weight. Now, if the planet is spinning very, very rapidly, there's this force outward, this centrifugal force, if you want to call it that. There's a lot of different ways you can calculate that. And yeah, if the planet's spinning really, really fast, that sort of counteracts gravity. And so you could have mountains that are taller than that. The limiting factor would be if you're spinning so rapidly that stuff starts to fly off the mountains. You have negative gravity on the planet. And if you go to a carnival, a fair, a circus, whatever it is, where you can get on the rides, and you can go on the spinny wheel and stuff like that. And it's spinning so rapidly that even if the wheel starts to tilt up, you're still plastered to the outside of that wheel, or you're on the inside. You feel this force outward that's stronger than gravity because you don't fall. It's the same thing. So if you had a planet spinning fast enough, yeah, you could have mountains bigger than that. But I have a feeling there would be other problems with earthquakes and your atmosphere flying away. I'd have to think about that, but that's really cool.
Sounds like you'd have to do some math.
Yes, sadly. And I have done stuff like this before because there are stars, neutron stars, for example, very dense, very small kinds of stars that spin incredibly rapidly. And they actually can distort and get egg-shaped because of this. And they can only spin so fast before flying apart. So, we do see things like that, but I don't know if planets can even spin that fast. It'd be interesting to find out.
Yeah, I mean, I don't think we haven't been able to measure the sphericity of rocky planets, close enough to see that yet. We see it with gas giants, for instance. Gas giants are oblate. They're, bit fatter at the equator than at the poles because they're spinning and they're made of gas, but that's not rocky planets and mountains. Right.
And Saturn is noticeably flattened. You can see it in pictures if you look at it. But in fact, I should say there are asteroids that do spin that fast. Complicated, we don't have time, but it's complicated. But asteroids can spin faster and faster and faster over time. And if they spin too fast, stuff off the surface starts flying off. And that basically steals some of the spin and it slows the asteroid down. So we do find a lot of asteroids, small ones.
Self-limiting, like you get to a certain point, you can't go any faster.
Yeah, and that's called the breakup speed. And we do find a lot of asteroids that are very close to that speed, which means this is happening. So that's a very good question.
I have another question from the chat from an anonymous attendee who says, what's the latest and or most interesting about the search for signs of life on exoplanets?
About searching for life?
Yeah.
What's the most interesting? We haven't found it yet. I think that's probably the thing. We don't know what's going on with these planets orbiting other stars. But what's happening, we're looking for planets. By we, I mean, Jessie, not me. I just write about what she does. But we're looking for planets that are like Earth, orbiting the right distance from their star so that they can have liquid water on their surface, for example, if they have an atmosphere and water. But it's hard to do that. It's sort of the cutting edge of what we can do. We can barely tell that some of these planets have atmospheres and sort of what's in them in general. So, being able to spot oxygen in the atmosphere of another planet is very tough. The JWST, the new telescope, may be able to detect that in some planets, and we'll see. There are a lot of observations going on right now to look for that. So anything I say about that may be obsolete in a week.
Right. The hottest off the press JWST result right now is that TRAPPIST-1b, which is the closest of those 7 rocky planets to the star, does not seem to have an atmosphere. They were able to get an emission spectrum of it. It just looks like bare rock. But of the 7, that was the one that was least likely to have an atmosphere because it's so close to the star that it's like, holding up a hairdryer to this planet. So it wasn't expected to have an atmosphere and it doesn't. So we're still holding out hopes for like the C and D and E that they might have atmospheres, but not yet.
Right. And I had a moment of panic. I mean, that paper came out a month ago or less. And I had a moment of panic. It's like, oh God, what did I write in the book? And it's flipping through the book, because I had an advanced copy. It's like, we're printed, this is done. Yeah. And it turns out I said it probably doesn't have an atmosphere. So I
saw that. I was like, yeah, well done.
But I think right now for looking for life, our own solar system is more interesting because we can explore it more thoroughly. And so we're looking at oceans of water under the surfaces of icy moons, Saturn, Jupiter, even Uranus, Neptune's moons, even Pluto might have liquid water under its surface. And of course, we have the Perseverance rover on Mars looking for it's not designed to look for signs of life, but it's kind of looking for the right environments, and future missions that are planned to look for life on Mars that may have existed billions of years ago. And I think that's we're probably going to learn a lot more about that sort of thing before we learn about what's going on with exoplanets. And I may be totally wrong here. We may launch a huge telescope in the next 20 years that finds, Proxima Centauri B has an oxygen atmosphere. That would be amazing. Well, C maybe. I think that's the right distance. But anyway, it's all of this is cutting edge, and the answer is we don't know. We don't know what's going on out there, but we may very soon, and that's the cool thing.
Yeah, that's very exciting. I'm told we have time for one more question, so I'll
Okay.
ask this one, and you can just yes or no this one. Do you anticipate that we'll find Earth-like planets?
Oh, absolutely. It's just statistics. I mean, we've hardly started looking, and we've found over 5,000 planets, and they're so weird. There's such a weird diversity of gigantic planets like Jupiter orbiting really close to their sun, planets that are in between the size of Earth and Neptune, and we don't even have planets like that in our solar system. They have atmospheres that are very different. And the thing is, we have found, and I don't know how many, you might know, Jesse, that are the size of Earth orbiting at that right distance from their star. And we don't know if they have atmospheres. We don't know if they're Earth-like, but they could be. And the fact of the matter is, especially around red dwarfs, which are the most common star in the galaxy, 70% of all stars are these little red dwarfs. And it looks like there's been a couple of papers that just came out that show that pretty much every red dwarf that we look at has planets and has more than one planet. And so just looking at the numbers, you're talking about probably over 1 trillion planets in our galaxy alone. The odds of there not being another Earth-like planet out there seem to be pretty slim to me. So I would bet, oh yeah, there are going to be other ones. We'll find them.
Yeah, I agree. And I think, unfortunately, that has to be the end of our chat. Thank you so much for chatting to us, Phil, about your new book, Under Alien Skies. The link is in the chat. Seth probably will do some mop-up, but it was really great to chat, Phil. Congratulations.
Thank you so much for doing this with me, Jesse. This was a lot of fun.
Yeah.
It's always nice to see you.
Yeah. Thank you both again for your time. This has been a fantastic presentation. I learned a lot. And yeah, like she said, the link to the book is in the chat. On behalf of Harvard University Division of Science, the Harvard Library, and the Harvard Bookstore, we hope you have a great night, and we hope to see you at our next event. And to the person who asked in the questions whether or not this will be available, this should be on our YouTube channel in a couple of weeks. So thank you all, and thank you both for your time. Have a nice night.
Thank you, Seth, and thanks everybody for watching.
Bye, folks.
Bye.